Parts-based programming basics. All of the techniques described here can be implemented using existing programming languages and tools. We commence by examining the requirements of non-programmers rather than focusing solely on the preferences of software developers. We begin by examining an exceptionally basic one-box node and arrow diagram. We consider the implications of this diagram for non-programmers. Subsequently, we gradually increase the complexity, progressing from one box to two boxes, then to parallelism. An implication is that language-supplied threads and operating system processes are not essential. Parallelism or green threads can be implemented using existing languages, including JavaScript. The concept of concurrency in programming languages is just a simulation of application-level concurrency. Even basic node and arrow diagrams cannot be built in a simple way when programmers adopt the functional programming paradigm from the outset. I present several techniques for augmenting programming tools with simple approaches to distributed concurrency. None of these techniques are particularly challenging. They are merely methods of combining existing techniques to program using diagrams. A simple node and arrow diagram. Data flows in from the left edge of the diagram and enters the left side of the box. The data gets processed. The processed data exits the box from the right and leaves the right side of the diagram. This is not how function calls work. Functions pass data, but functions also pass control flow. The caller expects the callee to run immediately while the caller waits. This is called blocking and requires extra code to support context switching in computers. Now we ratchet up the complexity to two boxes. We see two boxes and three wires. Data flows in from the far left. Data gets processed by box 1. Then data flows from box 1 to box 2. Data gets processed by box 2. Data flows out to the far right. Many programmers assume that this is the same as a pair of functions. In fact, what is shown on this diagram are three routines, box 1 and box 2, and a coordinator which shepherds data as indicated by the arrows. Using functional programming, many implementations of this simple pipeline fold the coordination code into box 1 instead of keeping it separated out. Box 1 calls box 2 instead of allowing the coordinator to determine the actual routing. While this conflation looks benign on the surface, it has deep implications on the psychology of programmers, which lead to buggy code for concurrent applications. Simply assume that box 1 sits inside an Arduino and that box 2 sits inside an ESP32 elsewhere. You can see that the Arduino code cannot call the code inside the ESP32 without elaborate workarounds. Yet, our programming languages assume that this is the case. Programmers have to resort to clumsy concepts like RPCs and to ad hoc uses of threading and messaging libraries to work around this inadequacy in their programming languages. Modern computer hardware is vastly different from computer hardware of the 1950s. Programming languages and notations and IDEs continue to express programs in terms of 1950s hardware instead of modern hardware. In the following slides, I show simple beginnings for augmenting programming to accommodate modern hardware problem spaces. Data flows in the direction of the arrow from the tail towards the arrowhead. The arrows represent data flow, not control flow, nor function calls. The data flows in only one direction. There is no implicit return. Explicit returns are possible, but only if the software architect draws them in as wires. Box 1 does not call box 2's port called in. Box 1 simply leaves a data message tagged out on its own output queue. The coordinator routes the message to box 2 and retags it with the ID in. Box 1 does not get to decide when box 2 must process the message. Box 1 is completely isolated from box 2. They are asynchronous. They are not implicitly joined by a call return thread of control flow. Calling implies synchronous operation that transfers control flow to the callee immediately. Leaving a message is asynchronous. The caller does not need to block waiting for the callee to respond. In fact, in an asynchronous system, box 2 might never respond to box 1 and instead may send data to a completely different receiver. The arrows do not actually touch the bigger boxes. The arrows just touch input and output ports. To be continued.